The other day in class, I shared with you the idea that when doing t-inference procedures, confidence intervals, tests of significance, you had to be mindful of the sample size. The idea was that if you're sampling from a fairly normal population, you can have pretty small samples, and then the sampling distribution will be nice and symmetric. It'll make a nice t-distribution. However, if you're sampling from a skewed population or a population that has lots of outliers, you really can't get away with small samples. You need larger samples, somewhere around 30 or 40. Depending upon the skewness. Things that are really skew require bigger samples. Populations with slight skewness, you really can get away with kind of a medium sample size. And so what I want to share with you are two applets that kind of illustrate that. And I've put links to them right in here in the Schoology folder for this week. This first one is a Rossman Chance applet, kind of a little older applet that's been updated. And then this is the second one's part of this Shiny Apps collection. So let me show you each of these and try to illustrate a few things. And you're welcome to kind of play with this on your own. First thing I'm going to do is look at the let's see, it's over here, the Rossman Chance one. This is really good for showing you the effect on confidence intervals and on the sampling distribution. So we're going to pick under method, we're going to pick means because we're talking about averages. And then this is the population, normal, say we're pulling from a normal population, and we're going to do keep track of a t statistic. And let's say that the mean is about 0.5 with a standard deviation of 10. And then let's make the mean something a little bigger. Let's say the mean is 50. And let's say that the deviation of the population is 10. And we're going to take a small sample, like maybe 10 items in the sample. And we'd like to know what happens to confidence intervals. Let's say we're going to do 95% confidence intervals. And I'd like this to go ahead and produce, let's say, 100 samples of size 10, and then build 100 confidence intervals from that. And so we're going to go ahead and select on sample, and we'll see what happens here. So okay, what this produces is it produces 100 confidence intervals, and they're all kind of drawn right here on the diagram. The ones in red are ones that did not capture the population mean of 50, and there are a few of those. And the ones in green did capture the mean of 50. And so this applet also keeps track of how many of the 100 samples will capture. Right now, 94%. So that's a good capture rate, pretty close to 95%. Here was the last sample of 10 items that were taken. You can see that this one, has a little bit of skew to it, but not too much. And again, that's fairly typical when you're pulling from a normal population. And you can see that the sampling distribution is fairly symmetric. And we're going to go ahead and keep taking more samples. So if you click sample again, now we have a collection of 200 samples. And here are 200 confidence intervals. And notice the capture rate right now stands at 93%. This was the last sample that was pulled. Of the 200 samples that have been pulled so far, this is the last sample. This is the distribution of the sample. And here's the sampling distribution. Now, over time, we expect this to kind of get more and more T-like. And so you keep clicking on sample. It'll grab a batch of another 100, and another 100, and another 100, and another 100. I'm going to take it up to 1,000 samples total. So after 1,000 samples, okay, we've got a capture rate, again, pretty close to 95%. So as expected, here was the last sample we took, and here's the sampling distribution, starting to get more and more T-like. And so if we kind of keep clicking this a few more times, we can take this up to Let me see if I can get this up to about 5,000 samples total. Let's see here, up to 35, 36. And again, I'm kind of watching this down here. This is after 4,000 samples. I'll stop there after 4,000 samples. I've got a pretty good capture rate, 95% as advertised. And this is starting to, kind of get more symmetric and more tea-like. Take it up to 5,000. Okay, and you generally get the idea. Okay, so normal samples you can get away with pretty small sample sizes of 10. But let's go ahead and reset all this, and let's suppose we had an exponential, which is a very skewed. Exponential population starts high and then gradually tapers off. We studied them a couple chapters ago, the exponential distribution, very, very skewed distribution. And let's say we have a mean of 50 and a deviation of 10. And let's see here. We'll take, again, small sample size, pardon me, so a mean of 50, we don't have a deviation here. We're going to take a small sample, 10 items, and we're going to take 100 intervals from that. Okay, so here we are at 100 intervals. And just after 100 intervals, you can see there's a bit of a problem. The capture rate is pretty low, 86%. And you look at the sampling distribution, although it's a bit early, you see it kind of skews off to the sides. Let's go ahead and take a couple more samples. Let's kind of maybe take it up to 2,000 samples total. And now we're up to 2,000 samples. And once again, our capture rate is kind of below the 95%. We're at 89%. You can see again, this is pretty typical when you pull from a really skewed population. You kind of get some outliers and some skewness over here. And again, you look at the sampling distribution itself, and you could see it's really not symmetric. It's kind of uneven. Now, of course, we'd have to kind of take more and more samples, but you'll kind of always have that sort of right skew in the sampling. Oop, that one's a little interesting. In the sampling distribution, and you really have to kind of maybe take this to a couple thousand samples before you can start to see the sampling distribution settle down. But another thing you'll notice, you're always kind of getting these samples that are again with outliers in them. That's kind of a telltale sign you're pulling from a skewed population. So instead of taking from 10, let's go ahead and reset. Let's take a bigger sample size again, and this is where some books will differ. Some will say 30 is large enough. I've been one to kind of lean more on 40. I'll split the difference and say 35. Let's take a sample size 35, and let's see what that does. So I'll take a couple hundred samples. All right, so we get up to about 4,000 samples here. After 4,000 samples, okay, you can start to see the capture rate, while not 95%, it is doing better at 35. And this is one of the reasons why I happen to be an advocate for 40. 40 does a little better job of getting you a bit closer to that 95% capture rate. Again, you look at a graph of the last sample, and it kind of skews. Pretty typical when you're drawing from a skewed population. And even still, this sampling distribution still looks to me like it has a little bit of skewness to it. And so you're welcome to try like sample size of 40 or 50 on here. But let's look at the other applet. It does a really nice job of showing the sampling distribution. So here I've started with a skewed population. And so right now it's extreme right skewness. And I'm going to take a small sample size. I'm going to take 10 items from here. And so now I think down here what I can do is, let's say I take, how many samples of size 10 would you want? I'm going to go ahead and take 10,000 samples. Instead of clicking a whole bunch of times on this applet, I can click, so I want 10,000 samples. And so now let's draw those 10,000 samples. Okay, this was the last sample that was drawn. Okay, again, the kind of an outlier in the sample, pretty common when you're pulling from a skewed population. But more importantly, here's the sampling distribution after 10,000 samples. You'll note a little bit of skewness right in over here, and not the mean is not quite in the middle. So you got a little bit of tailing off here with a sample size of 10. Now on this applet, what you can do is you can adjust the sample size and you can watch how this sampling distribution changes. So let's take it up to, say, a sample size of 20. Okay, and so after samples of size 20, 10,000 samples of size 20, here's your sampling distribution. Again, just a little bit of skewness right in here. Let's take it up to 30, which again, some authors propose that 30 is an adequate sample size for dealing with the skewness. And you know, you can say, oh, that's starting to look pretty symmetric, pretty T-like. Others might go, I don't know, I see a little difference here. And then let's go ahead and take it up to 40, which again is maybe a little conservative, but 40. And now you start to get an even better, you know, a little more symmetric. Notice how the sample averages are kind of really landing near the population average right there. And so this illustrates the idea that when you take, for really skewed populations, okay, you want to take larger samples. Like, how do you know you have a skewed population? Well, again, you look at the distribution of the sample you received, and when you start to see skewness, big skewness in the sample, and more importantly, when you see outliers in the sample, that's a good indicator that you've been drawing from a skewed population. So again, you're welcome to play with these and see how the effect of sample size, and pay especially close attention to, you know, how it affects the overall sampling distribution, and also the idea of what it does to capture rate. On the assignment, there's actually a really good video done by the folks at AP. One of the college presenters talks more about this idea of the effect of sample size and what it does on the capture rate. So thanks for watching.